In this last video of Lecture 2, I want to continue with different sensor characteristics. And I'm going to specifically introduce several resolutions. Okay, the first one is spatial resolution, the size of the field of view, or the actual size of the real world represented by one single pixel in your image. Okay, then spectral resolution. It is the number and size of spectral regions the sensor records data in. Okay, it's relatively complex than spatial resolution because it's twofold. Okay, number and size of spectral regions. The third one is temporal resolution, how often the sensor acquires data from the same area, Okay, and the last one is called radiometric resolution. We have discussed this a little bit before. It was called brightness value. If you go back to the first or second video of this lecture, I can't remember. So radiometric resolution is the sensitivity of detectors or sensors to small differences in electromagnetic energy. Okay, let's go through them one by one. I will provide some examples and more detailed explanations for these resolutions. So spatial resolution is relatively straightforward for understanding. It's a matter of the smallest angular or linear separation between two objects that can be resolved by the sensor. Because the smallest unit in an image is pixel, so pixel size is actually the direct indicator of spatial resolution. So examples here. 1, 2, 3, 4, 5, 6, 7, 8 images for the same area in the real world. So the first image here is very clear. We can say trees, tree canopies, road, and the houses, and we can also observe the shadows of vegetation of houses. We can also see there are cars right in front of houses. So each pixel here represents a very small area in the real world, which is 0.5 by 0.5 meter. In other words, 50 centimeter by 50 centimeter. That is the real world area addressed by each pixel in this image. That's the reason why you can clearly say even small objects such as a car or even a garbage can there, right? But for the same area, if the spatial resolution has been decreased from 0.5 meter to 1 meter, less details can be seen. But compared to 0.5 meter, it's not that dramatic. But if you do this continuously to 2 by 2, 5 by 5, you can obviously say that all those objects, they have been called pixelized because their shapes are not that real anymore. We can see small squares on boundaries between objects. For example, boundaries between houses and the surrounding vegetation, right? We can see small squares there. And if you continue to do this to 10 by 10 meter, 20 by 20 meter, from 20 by 20 meter, you cannot even tell if there are houses or roads or vegetation here. If it is 80 by 80 meters, you will see only pixels with different grayscales. So obviously, the higher the spatial resolution, the better the accuracy or the clarity of an image. But you should know that higher spatial resolution usually means more advanced sensors, which means high quality and high expense, which means you need to pay more money for that. And sometimes it's not necessary to have an image as accurate as this one. it actually depends on your application, depends on your research purpose, depend on what you would do with this image. Sometimes we don't need so much detail. So you cannot say that a high resolution is always better. No. And another problem is that usually high resolution images, they use a lot of computer storage space. Okay, and which means higher, much higher computational computational load, which means require more advanced computers to deal with larger hard drives to store them. So the higher the spatial resolution, the more details you have for sure, but you always need to find that a balance point between what you need and what you have. Okay. And another example for different spatial resolutions. Again, it's the same area from different sensors. ICONOS it's a sensor with 4-meter spatial resolution and 8 meters after 15 meters. You can see the difference here. So next, I want to talk about spectral resolution. This one is relatively complex, but not hard to understand, okay? So like I said, the concept of spectral resolution is twofold, okay? It is the number and dimension of specific wavelength intervals or ranges or bands in the electromagnetic spectrum to which a remote sensing instrument is sensitive. So if we have two sensors, sensor A and sensor B, sensor A has 10 bands that it can observe. It can retrieve information from 10 bands. Sensor B has 200 bands. Obviously, the number of specific wavelength intervals from sensor B is much larger than sensor A. So from that perspective, we can see that sensor B has higher spectral resolution in terms of the number of bands. Okay, so let's check this figure A. So for the top figure here, we have Landsat multispectral scanner. It's a sensor. It's called MSS. So it has 1, 2, 3, 4 bands. Band 1 green, band 2 red, band 3 near infrared, band 4 is for near infrared, also near infrared. But band 3 is near infrared from 700 nanometer to 800 nanometer. Band 4 is from 800 nanometer to 1100 nanometer. So how about ADAR 5500? Also 4 bands. Band 1 blue, band 2 green, band 3 red, band 4 near infrared. So in terms of number of bands, MSS and ADAR 5500, they have the same spectral resolution. But let's focus on the second aspect of spectral resolution, which is the dimension or the width of specific wavelength intervals. For MSS, green band is from 0.5 to 0.6 micrometer or 500 to 600 nanometer. So the width here is 100 nanometer, right? How about the green band from ADA 5500? It's from 0.52 micrometer to 0.6. Obviously, this wave here for green band is what? Is smaller than the green band from MSS. which means that the spectral resolution of green band from ADA 5500 is better than MSS because the green band from the former one, from ADA 5500 is what? Is narrower than the green band from MSS. It's similar for R band, right? R band, band 3 from ADA 5500 is narrower than the red band from MSS. Okay, so if we want to compare spectral resolution, you need to, if somebody is telling you the spectral resolution of a sensor, you should be careful with that. Is he talking about the number of bands or the width of each band? Of course, the larger the number of bands, the better the spectral resolution. But when we're talking about the width, when we're talking about the width of each band, the narrower the better. The narrower the band, the sensor, the better ability that this sensor has to detect small changes in reflectance. Okay, so figure B, here we have a specific a plot for the explanation of the width of each band. For example, here we have a specific band. I'm not sure which band this is, but let's just assume this is a specific band. And horizontal axis is for wavelength from 0.6 to 0.9. Okay, and we can see that the intensity or the ability of receiving energy of this band changes as the wavelength increases. So this sensor actually can receive a little bit energy from 0.5 maybe to 0.65, but the intensity can be received by the sensor is very low, which means it's useless. Which means this sensor can barely sense the information from this part of the spectrum. But beyond that, the ability of receiving energy increases dramatically. And around 0.75, that's where this band can receive most energy. And after that, its ability to receive energy drops dramatically again. So which means that, okay, only the energy from 0.7 to 0.8 can be effectively received by this band. So we use something called FWHM. Full name is full width at half maximum. At half maximum means the intensity of the energy can be received by this band is 50. Okay, if you draw a horizontal line here, here is the intersection, here is another intersection. So this FWHM is used to define the width of a band. Okay, for this specific band, the width is 100 nanometer band width, or simply width. Okay, the narrower this band width is, the better a sensor is. Okay, later I will tell you why. Okay, figure C here is a single band of ADA 5500 data. It's a I think it's a residential area, right? Because we have houses, and here maybe a business building right here, because we have a huge parking lot surrounding it, and of course we have 1, 2, 3 houses here. Okay, and you can see that because ADA 5500 has 1, 2, 3, 4 bands. So for the same area, it can produce 1, 2, 3, 4 images for all these 4 bands: blue band, green band, red band, and near infrared band. Okay, so in the next slide, I'm going to tell you why the narrower the band, the better the sensor. Okay, here, let's just say we have a spectral curve of vegetation. Okay, so horizontal axis is spectral wavelength. The vertical axis is for reflected energy. So we can say that this is a signature curve of vegetation in terms of reflected energy. Now we have a specific band, band A. It's from sensor A. It is relative. It is not relative. It's very wide. It covers a wavelength from here to here, and within this range of wavelengths, it actually covers a huge signature of this curve, because you can say the reflectance of vegetation increases dramatically within this range and becomes stable. Dropped a little bit, but stable. And A is covering this whole range, including this change, this turn here. And for each band, there is only one rating, which means that, okay, within band A, you have only one rating. You cannot say the difference before the turn and after the turn, okay, the turn of this curve. How about another band here, band B? Compared to band A, let's just say band B is from sensor B. Of course, one sensor can have multiple bands, but usually multiple bands in one sensor, they usually have the same band width. Usually, okay, only usually. Band B, of course, is narrower than band A. Actually, band A contains 3 to 4 band B in terms of its band width. So band B can only cover a small range of wavelengths. But if we use another band B on the right side of this current band B, we use 2 bands to have 2 ratings. We can obviously be relatively easier to catch the difference, the change of what? Of spectral curve. So here we have band C. So if you compare band A, band B, and band C, which one has the highest spectral resolution? Obviously B. Obviously B. Okay. If we use 3 B bands, or we can say if we use the resolution, spectral resolution of band B to what? To cover the same area now covered by A, we can have 3 or even 4 ratings. So more ratings can be used to catch small changes of what? Of the change of reflectance along the curve. Okay, so that's the importance of spectral resolution. More bands, okay, good. But for each band, the narrower the band, the better the sensor. Okay, and more examples here. For example, for TM sensor, from 400 to 900 nanometers, there are 4 bands, and there are gaps, which means at specific wavelengths, there is no band designed in TM sensor. On the other hand, let's just check another sensor is called average. From 400 to 900 nanometer, same range. There are 50 bands, and these bands, they are continuous in terms of the wavelengths of the electromagnetic radiation. So if we use 50 bands to capture the spectral signature, it is much better than TM, because TM can only use 4 bands to cover the same wavelength range, and there are gaps. With average, there is no gap. And at the bottom here is we call it data cube. For TM, we have 4 bands, so we have 4 images for a specific area. If you have 50 bands, like average, or even more bands, here we have 224 bands. which means we have 224 images for the same area. This this images, more than 200 images at different bands, they can actually catch most changes in reflectance from 400 nanometer to what? 2500 nanometer. So we have a continuous image or data cube here. So today, I'm not sure if you have heard a word, it's called hyperspectral remote sensing. That hyper means what? Means very high spectral resolution, which means we have a lot of bands, dozens or even hundreds of bands to capture every detail of the spectrum of a specific object or multiple objects on the ground. That's why it's called hyper, because the spectral resolution is pretty high, and spectral resolution includes two things. First one, number of bands. Second one, the width of each band. Okay. Okay. So another example here. Again, we have three curves here. Reflectance curve from 400 meter to 2600 nanometer. Okay. Curve 1, this short one, is for water. Curve 2 is for vegetation. Curve 3 is for soil. Okay. Now we have different sensors on the top. Landsat MSS, we have 1, 2, 3, 4 bands, and the last one is pretty wide, right? So MSS can only capture the signature of these curves from here to here with 4 bands, each one very wide. Landsat ETM Plus is better, 1, 2, 3, 4, 5, 6 bands. It is covering longer range of wavelengths, but the bandwidth for each channel, for each band is still very wide, right? It's pretty wide. Similarly, for NOAA AVHRR and for SPOT, which is a European sensor, 4 bands, AVHRR within this range, because it's for climate. This sensor does not require so many bands, so 2 bands. How about average? Dozens of bands from 400 nanometer to what? To 500 nanometer here. Continuous and dozens of bands, and the spectrum and it reflects these bands. They are addressing a very continuous reflectance spectrum. Okay. Next, temporal resolution. This one is very straightforward. It's also called revisit period or revisit time. It means the time interval between two successive visit for the same area. For example, a satellite is flying over a specific area. Let's call it area A on June 1 of 2001. Okay, and it is going away. We're talking about a satellite with a polar orbit. Okay, and next time when it revisits the same area, it is on July 17th of the same year. So the interval is 16 days, right? So the temporal resolution for this satellite, or you can say for this sensor, is 16 days. Okay, so when is the next visit? You just need to add 16 days to July 17, which is, June 17, which is July 3rd of the same year. Okay, so this is temporal resolution. So here are some examples of temporal resolution for famous sensors or satellites. NOAA AVHRR. Series twice a day, morning and afternoon. Oh, you will say, why is it so fast? Why is it so fast? Because there could be one sensor on multiple satellites. Okay, And a mod is EOS mod is once daily. Okay, Landsat is 16 days. 16 days. Spot HRV is 26 days. Okay, but locally flexible could be but locally flexible 2 to 3 days because it has two modes. I'm going to introduce this sensor family later in this course, okay? And the space imaging ICONOS, 3 days max. Digital globe, that's space imaging and the digital globe, they are company names, okay? They are commercial satellite companies. Digital globe has QuickBird, which is 2.5 days max. Why would I say max? Because it's commercial. If you pay real money, they can adjust the orbit of the satellite for you. Okay, it could be a lot of money, but they can do that. So their revisiting period or temporal resolution can be changed. So 3 days max, 2.5 days max. So the last resolution I want to discuss here is called radiometric resolution. It is the sensitivity of remote sensing detectors or sensors to small differences in EMR. So if a if a sensor's radiometric resolution is 256, it means that the sensor uses 8-bit mode to record data. 8-bit of what? 8-bit of binary figure. So each figure can be 0 or 1. So how many combinations are there? 2 to the power of 8, which is 256 combinations. Of course, if you use 9 bits, okay, you have 512 possible brightness values, or even better, right? I think this one is relatively straightforward to understand. So let's see some examples, right? If you are using 8-bit quantization, you have 256 grayscale levels. So in this image, we can say here we have water body because I can say there are bridges and docks, I think. And we have roads, a main road here. We have small roads everywhere. We have some tanks here, could be gas tank, could be water tank. We have a huge building here surrounded by small buildings. So grayscales here are very abundant. We have 256 levels. And this is 8-bit. If we change it to 6-bit, to 4-bit, to 3-bit, you can say less and less grayscales, less and less levels of grayscales can be used to address the same area. As a result, you can say less and less details here, right? From 8 to 6 to 4 to 3 to 2 to 1. What does it mean by 1 bit? 1 bit means that you can use only one figure to address your image, right? One figure binary, that's 0 or 1, correct. We only have black and white in this image, and you cannot recognize or identify any land cover type here or any objects here on the ground. It's just white and black patches. If you compare this 1-bit quantization to 8-bit quantization, so 2 levels versus 256 levels of grayscale, huge difference, right? So here, of course, 8-bit and 1-bit is just too extreme, okay? But here you can see the importance and the meaning of radiometric resolution, okay? The higher the resolution here, of course, you can use levels to address resolution, or you can simply say the radiometric resolution of this sensor is 8-bit. right? Usually, a beat is more commonly used. We say it's an 8-bit sensor, 6-bit sensor, or 4-bit sensor. You use levels, okay, people know that. But yeah, that's just 8-bit. So 8-bit, 6-bit, or even you can have a 10-bit or 12-bit. Yeah, it can be even better. But yeah, if you compare them, you know the meaning and the importance of radiometric resolution. The higher the bit number, the more detail can be provided by the sensor. Okay, here is a list of most famous sensors around the world with different spectral, spatial, radiometric, and temporal resolutions. We have coarse resolution sensors. Here, coarse resolution refers to coarse spatial resolution. Okay, multispectral sensors. Multispectral here means the spectral resolution. Okay, so usually you can say spectral resolution here, no more than 15 bands. So here, hyperspectral sensor, it means this sensor has a lot of bands. How many? 196. Okay. We also have hyperspatial sensor. It means that the spatial resolution of these sensors is pretty high. The spectral resolution is not even high. 4 bands, 3 bands, 5 bands, only 1 band. Panchromatic means 1 band for all colors. It's just like the camera on your phone. Okay, the camera on your phone is a panchromatic sensor. You can just consider it that way. And we have 4 bands, 5 bands, and 5 bands. So all these sensors, I'm not asking you to memorize their spatial, spectral, radiometric, and temporal resolutions. At least among them, most famous sensors among them should be memorized. Okay, it's the basis for a student or a scholar in remote sensing area. Okay, AVHRR, MODIS, Landsat family, they are famous. They are very famous. Okay, Landsat family, Hyperion, Iconus, and QuickBird. These last two, they are famous for their extremely high spatial resolution and they are very successful commercial sensors. Okay, that's all I want to say for lecture 2. Okay, I will see you in the next lecture. Thank you.